D is the correct answer. How come? Well, how come is this. How much does a mole of water weigh? 18 grams. 18 grams is how many milliliters? 1 gram of water is approximately how many milliliters? 1 milliliter. So 18 grams is 18 milliliters. And so 1 mole of water is 18 milliliters. 2 moles of water is 36 milliliters. 4 moles, 72 milliliters. 72 milliliters is this, and then to make it liters, you move the decimal 3 over, and then you get 0.072 liters. So 72 milliliters is the correct answer. And so that's D, because it's liquid, so liquids we have to handle differently. 7, a device used to measure the atmospheric pressure. Barometer. 1 liter of air, 80%, this is approximately 80% nitrogen, at 1 bar consists of 1 liter of nitrogen at a pressure of 0.8 bar. Is that true or false? True. Yeah, it's true. 1 liter of air. 1 liter of air consists of 1 liter of nitrogen at a pressure of 0.8 bar. And 1 liter of oxygen at 0.2 bar. Sure. 9, 100% humidity at 25 degrees C means the air is supersaturated with water vapor. That's false. It's false. Supersaturated has a specific definition in chemistry. This is not it. This would be considered saturated, not supersaturated. Supersaturated, we have to go over 100% humidity. It's unstable. 10, 1 liter of air, 80% nitrogen at 1 bar consists of 0.8 liters of nitrogen at a pressure of 1 bar. Is that true or false? That's true also. And so number 8 is an example of Dalton's law. Number 10 is an example of Avogadro's law. You know, what Dalton said is that the total pressure is equal to the sum of the partial pressures. And so P total is equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, dot, dot, dot. Well, Avogadro's law says that the V total is equal to the sum of the partial volumes. So the volume of gas A plus the volume of gas B plus dot. And the restrictions here is, you know, for Dalton's law to work, the volume must be constant. So everything must have the same volume. The air, the nitrogen, the oxygen, everything has the same volume. Whereas for Avogadro's, the pressure has to be constant. So everything has to have the same pressure. The air, the nitrogen, the oxygen, everything has the same pressure. That's 10. 11, 0.8 liters of nitrogen at 0.8 atmospheres plus 0.2 liters of oxygen at 0.2 atmospheres gives 1 liter of air at 1 atmosphere. It's false. This is false. You can't mix them. You either have to stick with Dalton's or you have to stick with Avogadro's. You can't, you know, we could switch it, like on one calculation we can use Avogadro's, on another calculation we use Dalton's, but we can't do it both in the same problem. 12 is just straight Dalton's. The total pressure of a mixture in millimeters of mercury containing oxygen at 736.2 and water vapor at 23.8 equals So Dalton's just says you just add up the partial pressures, add up the pressure of the oxygen plus the pressure of the water, and that is going to give us a total pressure of 760. Solids form crystalline or amorphous structures. Sure. Vapor pressure is the equilibrium between liquid molecules vaporizing and vapor condensing. So D is the correct answer. Good. 15. Select the species expected to have the highest vapor pressure. Yeah, alcohol. Alcohol would be the most volatile. The highest. Select the species expected to have the highest heat of vaporization. Syrup. Yeah. 17. Water can boil at 25 degrees C. Well, at what temperature does water boil? Water boils at 100 degrees C. Is that correct? But not always. Does water boil at 100 degrees C in Denver, Colorado? Not always. You know why? Because the boiling point of water depends on what atmospheric pressure is. If we have normal atmosphere, what is normal atmospheric pressure? 1 atmosphere. So if the atmospheric pressure is 1 atmosphere, then the pressure pushing down on the liquid is 1 atmosphere. So we need a pressure pushing up of 1 atmosphere, and then we have boiling. And so the pressure pushing up is the vapor pressure. And so if we look at the vapor pressure of water, it increases until it hits 1 atmosphere, and it matches atmospheric pressure. That's what we call the normal boiling point. So the normal boiling point of water is 100 degrees C, of ethanol is 78.3, of diethyl ether is 34.6. Those are the normal boiling points. But atmospheric pressure fluctuates. Some days it's lower, some days it's higher. So as atmospheric pressure fluctuates, that's going to move the boiling point, since all we have to do is match atmospheric pressure. And so it is possible to boil water room temperature. Room temperature would be down here. If we lower the pressure, what do we have to lower the pressure to? Not really shown very well in this one. We can boil water at 25 degrees C if we lower the vapor pressure to around 30 torr. A vapor pressure around 30, 32 torr will do it. That way, you know, if you don't have much pressure pushing down, then we don't need much pressure pushing up, and therefore we don't need much temperature. And so it is possible to boil water at room temperature. We need to use a vacuum pump to generate the lower pressures. And so this is just showing how we can boil water at room temperature by using a vacuum pump. Here. Right now the water is not boiling because the pressure is 1 atmosphere. Lowering the pressure by sucking the air out of the flask. You see the water starting to boil there? There's no heat involved except room temperature. So water can boil at 25 degrees C? That's true. Yeah. This is why they have high altitude cooking instructions. High altitude atmospheric pressure is lower. Atmospheric pressure is lower than the boiling point is lower. If the boiling point's lower, it takes longer to cook food. So if you were to cook pasta at room temperature with a vacuum pump like that, boiling the water, how long would it take to cook the pasta at room temperature? Well, it's the same thing as putting pasta into a room temperature pot of water. How long is it going to take to cook? Take a while, yeah. So you have to add time. So there's a rule of thumb in chemistry. For every 10 degrees C temperature, let's say 10 degrees C drop in temperature, so water normally boils at 100. If you tried to boil pasta at 90 degrees C, it would take twice as long. So you have to double the cooking time. The opposite's true too. Pressure cookers. If you have a pressure cooker, then we can increase the pressure. So if you have a pressure cooker, then the atmospheric pressure inside the pressure cooker is going to be higher, which means in order to match it, the temperature of the water has to be higher. And if the temperature of the water is a little higher, let's say 5 degrees higher, then it's going to result in a much faster cooking time. Pressure cooker. And so we need some kind of fixed reference point. The fixed reference point is normal, the normal boiling point, but the boiling point can be anywhere along the line here. The water. Which has a lower surface tension, soapy water or water? Soapy water. Which species is expected to have the highest viscosity? Syrup. The boiling point is defined as the temperature at which the liquid is found to boil. That's true. It's not the most comprehensive definition, but satisfactory. All things being equal, rank the IMFs weak to strong. Which one? D. 22. Select all IMFs present in acetic acid. H bonds, yes. Acetic acid, CH3, COOH. So CH3, COOH. So we have H bonds. In fact, the H bonds in acetic acid are pretty strong, especially to other acetic acid molecules. Take a look at this. Do you know what this is? This is showing two acetic acid molecules. There's one on the left here. There's one on the right here. And they're being held together. Do you know what they're being held together primarily by? H bonds. These dashes are H bonds here. In fact, this is so favorable. What tends to happen is if you have acetic acid in water, the acetic acids aren't independent. What typically happens is a lot of the acetic acids will pair up like this, and then they'll move together as a pair rather than two separate acetic acid molecules because they're so strongly held together. This is called a dimer, an acetic acid dimer. It's like a pair. And until there's a collision comes, it can break them apart. You know? Otherwise, they'd like to go around in pairs. But it all depends on the temperature too. You know, higher the temperature, the more kinetic energy, less this dimerization is going to happen. This is another slide showing dimerization. Here's another file, acetic acid cyclic dimer. So this is, I just searched acetic acid dimers. And so lots of images of acetic acid dimer, the H bonds holding, but H bonds aren't the only thing that hold. Two acetic acids. The lone acetic acid molecule is called a monomer, a dimer. Sometimes these things are held together by actual bonds. If they're held together, then we can form like polymers. There are other attractions present. What are they? Yes. Dipoles. Dipoles because, well, H bonds are a usually big dipole. Hydrogen bonded to oxygen, that's a big dipole. But we also have this permanent dipole here, which is carbon-oxygen dipole. And then we have dispersion. Anything with electron will have dispersion forces or instantaneous dipoles. Anything with electrons can at one instant in time polarize.
So all of them.
And so all of them. If it's all of them, which ones do you mark on the scantron? Which ones do you mark on the scantron are all of them? Yeah, it's usually T, all of the above. But in this case, you can bubble more than one. Did you know that?
Yeah.
And so bubble A, B, and C on the scantron. Only do that if there's more than one answer. If there's only one answer, then you're automatically going to get wrong. 23, all IMFs are electrical attractions. True. CHF3 has the potential of a hydrogen bond. CHF3. When hydrogen is bonded to fluorine, oxygen, and nitrogen, it can hydrogen bond. But sometimes how the formula is written is deceptive because that hydrogen is not actually bonded to fluorine. That hydrogen is bonded to what atom? Carbon. So the hydrogen is actually bonded to the carbon, and the fluorines are bonded to the carbon as well. There's going to be 4 bonds. And so in this case, what are the IMFs present? No hydrogen bonding. The hydrogen has to be directly bonded to the fluorine. It's not. It's bonded to the carbon. And hydrocarbon bonds are nonpolar anyway, or close enough to nonpolar to call them nonpolar. Do we have dipole? Yeah, dipole's present and instantaneous dipole or dispersion. So those two are present. Ice is an example of an amorphous solid.
False.
False. So the other day I showed you some ice crystals, like this. You look at the ice crystals, they're very nicely ordered. Ice crystals, Wikipedia, it's close up. Sometimes if you catch a snowflake and look at it closely, this is what a snowflake looks like. Nice crystal of ice. But, you know, a lot of people try to make things that are amorphous because it gives them different properties. So one of the big ones is quartz. Quartz crystal, right? This quartz crystal, and there's another thing called quartz glass. Quartz glass is amorphous, quartz crystal is crystalline. And they have different properties, totally different properties. And so, quartz crystals called quartz and quartz glass or amorphous quartz is sometimes called fused silicon. Which can be used in glass blowing. Anyway, well, has somebody tried to make amorphous ice? Normally when people think about ice, they think about nice crystals like this. But essentially what an amorphous solid is a frozen liquid. So is it possible to freeze the water so fast it doesn't have time to organize into a nice crystal? And the answer is yes. People have tried to make amorphous ice and have been successful in making amorphous ice. I'm going to put this slide. So for example, here, structure of a new dense amorphous ice. The detailed structure of a new dense amorphous ice, the BHDA, is determined by neutron diffraction. These will have interesting properties that might be useful. Let's see. So, if you argued that there is such thing as amorphous ice, and he showed me, I would give you credit for this one. But typically we say true or false. We say false. Covalent crystals are typically hard with high melting point. True. Sugar and water is a homogeneous mixture. Sugar and water. Homogeneous mixtures of sugar and water are called solutions. Like dissolves like for molecular compounds. That's true. Which should be the most soluble in water? Which one is it? A, CO2. What happens when you exhale underwater? Does the CO2 dissolve? No. Would it be C because there's more hydrogen? No, it would not be C because there's more hydrocarbon. Hydrocarbons are like gasoline. Gasoline is a mixture of hydrocarbons, like oil, like methane. Is methane very soluble in water, or does it bubble out of water? It bubbles out. And so this is more, you know, when I look at this part is like water. This is an alcohol.
Yeah.
So this part's like water, but this part is like oil. And when I think about it, oil and water don't mix. This is called butanol. Butanol, we predict it's not going to be very soluble in water. In fact, let's take a look at the data here. Butanol, also called butyl alcohol, is a 4-carbon alcohol with this formula. Let's just scroll. The one we're looking at is called N-butanol. N-butanol has limited solubility. It's not very soluble. So when I look at this one is more water-like because it has less hydrocarbon. This one's called ethanol. In fact, ethanol, it's okay. You know, just having that 2 carbon chain is not that significant because ethanol is what we call soluble. But we give it a special name. It's so soluble, we call it miscible, right? It's infinite. In fact, ethanol is infinitely soluble in water. Just like methanol. Methanol is infinitely soluble in water. Very water-like. Ethanol is. But when we get to butanol, no. Pentanol is even worse. Pentanol is not. Pentanol is starting to look more like hydrocarbon. Solubility of oxygen in water increases with increasing temperature. Well, what happens, let's say CO2. Let's say you have a sparkling water. What happens if you increase the temperature of sparkling water? It goes flat. It goes flat quickly, because the solubility of CO2 goes down with increasing temperature. It's harder to keep it in the water. It's harder to keep a gas in water at high temperatures because of all the kinetic energy. And so the same thing with oxygen. Are the fish going to be more happy in hot water or in cold water? There's going to be more oxygen in cold water. Maybe not too cold, but you know. But if the water gets too hot, then there's going to be very little oxygen in water because too much kinetic energy. 32 is an equilibrium problem. We'll skip that. 33, we should be able to do that. A solution is made by mixing 5.23 grams of sugar with 94.77 grams of water. What is the percent composition by mass? So the percent sugar is going to be 5.23 grams of sugar over the total grams. What is the total grams? Is it 94.77 total grams? No, 94.77 is just the grams of solvent. The total grams would be the solvent plus the solute. And so it would be 5.23 plus 94.77, which gives us 100 grams. And so out of that 100 grams total, 5.23 grams is sugar and 94.77 grams is water. That's sugar water. And so what is the percentage? 5.23 out of 100 would give us 5.23%. Multiplied by 100%. So the correct answer is 8. Okay, let's take a break and then we'll finish this up.